Okay, now we're at section 23.2, electric flux, and let's share the PowerPoint. And there you have it. We have the orange is, of course, the orange arrows are electric field lines, and they're going through an area A. So you can see that there's an E, the electric field passing through an area. So the flux, the flux is the electric flux. We're going to talk about magnetic flux in a few more chapters. So here you have the electric flux is equal to the electric field times the area that it passes through. Pretty straightforward. So right here, you can see the electric field is going, all of the field lines are perpendicular to the area that is crossing. But what if we have an area that is not perpendicular to? The number of field lines that go through the area A perpendicular, that's that little perpendicular part down here, W perpendicular, it's the same as the number that go through area A. So the area is equal to LW, and I want to caution you because I was looking at this and I was confused. They explain it well in the book and also in the I mean, it's a little deceiving. And let me explain why. I struggled this myself when I first looked at it, because this W here looks like it's applying to this this piece here, and it's like, you know what, that's the opposite side to the hypotenuse, but it's really what they're talking about. This W, I wish they would have made it a little closer to this section here. Let me make that a little thicker. They're talking about W is this here. That's W. The W looks like it's pertaining to that dash line, but it's not. This is the W. It confused me for a bit. So the area is equal to, of course, L times W. W perpendicular is this section here. This, let's just make it. This is the cosine of W is the hypotenuse, so W perpendicular is W cosine theta. So the area perpendicular, that perpendicular area that's hanging down, is equal to LW perpendicular times LW cosine theta. So the area is equal to LW is equal to the area. So A perpendicular is equal to A cosine theta. So the flux through that perpendicular area is equal to E times A perpendicular, and that's equal to E A cosine theta. So the flux is also, I don't particularly care for this definition. They're saying it's the cosine theta projection of the electric field. Well, the electric field is just going straight. There is they're talking about the electric field that's normal to the surface. Well, there is no electric field that's normal to the surface A. There is to the A perpendicular, and a normal here is you can see it here. It's this. Well, that didn't come out very well. Let's try it this way. You follow my red here. It doesn't work very well. It's probably it's not snapping to a point that it likes. There it goes. The perpendicular is the normal is that vector that is perpendicular to the surface A. That's what the normal is. Now I need to go back to the, oops, wrong one. I not change it there. Let's change it here on the, now we can go through those. A equals LW, W perpendicular is W cosine theta, LW cosine theta, the LW is the area, so the area perpendicular is A cosine theta. I mean, it's the area times cosine theta, so it's reduced by a cosine theta term. The flux is EA perpendicular, which is EA cosine theta, and for that little last one, it's the normal component of the electric field through the area. And again, I don't particularly care for that definition, but that's okay. And let's let me look at these notes here. You on left. Okay. Now the electric field makes an angle theta I with a vector delta AI defined as being normal to the surface element. Whenever we talk about the surface normal, you're talking about a wherever the surface is. Even you take a little section of curved surface, you can find a normal to that surface that is the vector that's perpendicular to it. So the flux, the electric flux for the ith position is EI times delta AI cosine theta I, because the theta is going to be changing. If you have a surface, the theta is going to be changing. If the electric field is emanating outward and your surface is changing, you're going to get different theta terms. So you've got a change in electric field, depending on where you are, a changing area, surface area, and a changing theta. So it's E I dot delta A I, and of course from the dot product, well, let me not jump the gun. So E phi E, the flux, the electric flux is approximately equal to EI dotted with delta AI. And so in order to get the entire electric flux, you take the surface integral of E dot dA. And we've had the dot product. The dot product, E dotted with A is EA cosine theta. I think that comes up later in the lecture. So let's look at imagine this football-shaped area. The blue surface is kind of an oval, egg-shaped football, whatever you want to call it, and there's flux lines going through it. Let's look at the first one. The electric flux through this area element is positive because the electric field is coming out of the area. It's emanating out of the area. The electric flux through this area element is zero. Remember, E dot A, the dot product is EA cosine theta. What's the cosine of 90 degrees? The cosine of 90 degrees is 0 degrees. Is zero. The cosine of 90 degrees is zero. So if you have EA cosine theta is equal to zero, the whole thing is equal to zero. So the electric flux through this area element is zero. When it's perpendicular, it's zero. And consequently, or the corollary is that if it's in line, if E is in line with the A, that's EA cosine theta where theta is equal to zero. If they're parallel, the angle between them is zero. EA cosine theta in that case is 1. So you get EA, that's your maximum. And then let's look at 3. the electric flux through this area element is negative. Why? Because it's going into the surface. So it's negative going into the surface, it's positive coming out of the surface. And so the electric flux is the sum of all these E dot dA, so it's E to the N dA, it's a surface integral. Okay, let's suppose a point charge is located at the center of a spherical surface. The electric field at the surface of the sphere and the total flux through the sphere are determined. Now the radius of the sphere is half. What happens to the flux through the sphere and the magnitude of the electric field at the surface of the sphere? Okay, now the rate is, so you have this point charge inside a sphere, a spherical surface. The electric field at the surface of the sphere and the total flux through the sphere are determined. Now the radius of the sphere is halved. What happens to the flux through the sphere? Well, the flux is the same because the number of field lines that you had coming out from the big one are still coming out of the small one. However, the electric field, as you're getting closer to the source of as you're getting closer to the source of the electric field, you're getting closer. The R is reducing, and so the field increases. The flux remains the same. You have the same number of flux lines going through the entire surface, and the field increases. The electric field increases because you're getting closer to whatever charges are causing the electric field. Okay, and I think, yeah, that's the next section. So we'll end this here.